Hello everyone, I'm Zhang Xingbian. Today, I'm going to present our work, a deformable image registration-based method to assess directionality of thoracic aortic aneurysm growth. The thoracic aorta is the largest artery in the body, carrying blood from the heart to the rest of the body. An aortic aneurysm is a disease where progressive weakening of the aortic wall leads to dilation of the vessel, and over time, the blood vessel balloons to a size that is at risk for bursting or delaminating. This can cause life-threatening bleeding and potentially death. So, the ability to accurately measure aortic growth and better predict complications is important. Currently, the growth is assessed by changes in maximal aortic diameter, which is manually done by humans and is subject to a significant degree of measurement variability. Previously, we proposed a method to assess 3D changes using B-spline-based deformable registration and Jacobian determinant. However, there is a growing awareness that directional aortic deformation is important, particularly longitudinal growth, such as elongation of the vessel. Thus, in this paper, our goal is to decompose the Jacobian determinant, which measures the 3D changes into several directional components, such as the longitudinal determinant and the cross-sectional determinant. This decomposition allows clinicians to isolate and study the pathological effects of each component separately. For example, we can tell what amount of deformation is caused by elongation and what amount of deformation is caused by aneurysm growth. To give a concrete example here, the transparent white model is the original aortic anatomy, and we created the synthetic deformation in region A, B, and C to get the deformed aorta, which is in the blue surface here. In region B, we created some compression, and in region A, we created some expansion. And these two deformations are mainly the cross-sectional change. Also in region C, we stretch the distal portion of the descending aorta to create the elongation. As you can see, when we use a previous technique to plot growth in the original determinant, it does a good job capturing the deformation, but it cannot tell us the directionality of the deformation. In contrast, when we use our method to decompose the Jacobian into, for example, the cross-sectional determinant and the longitudinal determinant, we can see in cross-sectional graph, the region A and B have predominantly cross-sectional change. However, in region C, we can see there is little cross-sectional change. However, looking at the longitudinal determinant image, we can visualize the isolated longitudinal deformation in region C that results from elongation. Then let's look at the framework in detail. Actually, it's quite simple. Given a pair of CT images, on the one hand, we register them to get the Jacobian matrix field. And on the other hand, we build a 3D model from the binary segmentation. And then we build a local coordinate system at each vertex of the 3D model. Then we applied algorithm 1 to decompose the original Jacobian into directional Jacobian component. And you can find the algorithm 1 in the paper. As for defining the coordinate system, we propose two types, the R type, which is based on the radial vector, and N type, which is based on the normal vector at each surface element on the mesh. Users can select either coordinate system depending on which is most appropriate for the desired task. Finally, to understand this technique will work outside of the synthetic experiment, we tested our method on two typical clinical cases with obvious longitudinal and cross-sectional growth. These patients have two CT scans performed at a 7 to 8 year interval to monitor growth. And we used our deformable image registration-based technique for quantifying the Jacobian matrix field as described above. On the left case, we can see it has a significant cross-sectional growth in region A, and for region B and C, we can observe longitudinal growth and compression just before and after an area of elongation and kinking that developed between the two CT images. In contrast, the case on the right has very minimal cross-sectional growth, but demonstrated a clear longitudinal growth in the region A and B, which can be easily seen by comparing two 3D models. In conclusion, we have demonstrated our method's ability to isolate measurements of cross-sectional and longitudinal aortic growth in both synthetic experiments and real clinical cases. We identified clear separation of regions with longitudinal and cross-sectional growth in clinical cases in a way that has not been previously described. We hope that our method can offer new metrics to assess aortic aneurysm progression and improve understanding of this disease.